Today we'll actually start with the introduction to organic chemistry. We have our saturated hydrocarbons that we're going to talk about first. This is one part of a three-part lecture on this chapter. We'll just introduce them today and get used to nomenclature and how things are put together. And then next time we'll move on to a little more detail on the molecules themselves and how they behave. And then the third part we'll talk about some reactions they undergo. Okay. So the first thing we want to do is define organic chemistry. And if you look at all the molecules out there in the entire universe, there's about 9 million of them we would call organic molecules. In other words, they contain carbon, right? Some molecule containing carbons and hydrogens. And then the rest of the molecules out there that do not contain some assembly of carbon, we call them inorganic molecules. And there are only about 100 or 1.8 million of those. And so there's about a 5-to-1 ratio here of organic molecules versus all the rest. So this is why this necessitated its own branch of chemistry, our own field of study. Because just so many ways carbons can make bonds. It's quite unique. Right? No other element can do this. So let's look at the specifics of carbon itself. It was on that second period or second row of the periodic table, which I had you memorize as part of the very small amount of the table I want you to know. Now, looking from left to right, we started with lithium on the far left over there under hydrogen. It had a total of 3 electrons, one of them being a valence electron because, as you remember, there are 2 in the lower shell that hydrogen and helium occupy. And then there's one more, so it's the only one in its outer second shell, or valence shell. And moving across the table, you had beryllium and boron, and we finally arrive at carbon with 4 in its outer shell. Yes, there are a total of 6 electrons and 6 protons, remember that. We'll ignore the neutrons for this course. But for the electrons, there are 2 in that inner shell again, leaving 4 for the valence shell. So you've gotten used to doing that. There'll be 5 for nitrogen, 6 for oxygen, 7 for fluorine, and of course all 8 occupied in the noble gas neon. So back at carbon, we have 4 in the outer shell, but all of these would love to get to a complete outer shell. In other words, have 8 in the outer shell, and that's why carbon would make 4 bonds. It shares 4 of its single electrons with other atoms that are also sharing an electron with it. Nitrogen would make typically 3 bonds, oxygen 2, and fluorine only 1 because it's already at 7. So carbon being at 4 is kind of halfway between being full and empty. It's got room for the most number of bonds that you can make among the elements in this row. So the way carbon does that, as you see in the diagram, we have 4 electrons in the outer shell or valence shell. That's why it's listed as electrons 2, 4. There's 2 in the first shell and 4 in the second. 6 protons in the nucleus, of course, which makes it carbon. And there's 6 neutrons, which we'll ignore because they don't get involved in the chemistry. So that one carbon can share each of its 4 electrons with another atom, which is also donating 1 electron, in this case for methane or CH4. Right? Each hydrogen also has 1 valence electron, and it's sharing it with the carbon as well. So like we said before, that shared pair of electrons we can draw as a line or a bond, and that represents how methane looks. Right? So this is how we would draw methane, and that's our simplest organic molecule, right? Made of a carbon chain or carbon bonds, in this case just the 4 hydrogens. Okay? We can get a little more complex, and that this carbon, instead of bonding to just hydrogen, could bond to yet another carbon. And that's shown down here in the bottom. Right? This is ethane. We'll talk about the nomenclature in a minute. But it's simply 2 carbon atoms bonding to each other. Yes, they are sharing a pair of electrons between them. And then each of those is sharing electrons with 3 hydrogens. Again, each carbon has exactly 4 bonds. That's always going to be the case. Carbon will always make 4 bonds. And carbon, for the purposes of this class, will never have a lone pair. Right? It's always going to make these 4 bonds. Now some of them may be in double bonds, we'll see in a second, but it'll always make 4 total bonds, never 3, never 5, and it'll never have a lone pair. Okay? There are some examples of lone pairs on carbons we won't talk about for this course. This is an introductory course, and once you see that, learn the basics first. So carbon makes 4 bonds. Not 3, not 2, not 5, not 6, exactly 4. Right? Now, they don't always have to be to hydrogen, of course. They can be to other elements, like you see down here. And in some cases, you could have double bonds between the carbons. We'll save those for a future lecture. But for today, I just want you to know that it can happen. So this carbon here still is making 4 bonds, 2 of which are to a neighboring carbon, and then 2 to hydrogen. There's still total of 4 bonds there. Now what's different about this molecule is the geometry. If you look back at ethane here, or methane for that matter, either carbon here having 4 single bonds, no lone pairs, has what geometry? Now, you may be thinking, hey, you didn't ask that question correctly. You should ask us, do you mean electronic geometry, or do you mean molecular geometry? And I agree, I should have said one or the other. But in fact, for this case, since there's no lone pairs, they're one and the same. So what is the electronic/molecular geometry here? So 4 single bonds, no lone pairs. What geometry is it?
Is it tetrahedral?
It is tetrahedral, exactly. So the way it's drawn on the page is not exactly how it looks. This is our 2-dimensional representation of it, how we've been drawing them. They aren't across from each other like in this picture. You know that they're a tetrahedral arrangement. Same thing in this little diagram over here. They don't look like this. It's not straight across. This is not the most stable conformation at all. So it's a tetrahedral arrangement, but I can't draw that easily on a 2-dimensional surface, right, without the wedges and dashes or some kind of 3D illustration. So we tend to draw them like this with these straight lines and across from each other, but keep in mind that if it's got 4 single bonds, or 4 Vesper groups, as we said, it's going to have a tetrahedral geometry. Moving on to ethene here, what's the geometry around this carbon? So this is all review from last time. What geometry would it have?
Trigonal planar.
Trigonal planar. And you got that because there are 3 areas of electrons. So this carbon over here, this hydrogen up here, and this hydrogen over here. In fact, this whole thing over here counts as one area with respect to this carbon. So it's got 3 Vesper groups, so no lone pairs, of course, on carbon. So trigonal planar geometry. So it doesn't look like you see it on the screen here, because trigonal planar would have a 120-degree angle between each of these, and this is drawn straight across. It's just a typical way we draw it sometimes. The best way to represent this one, since I can do it on a piece of paper, is to put the carbons like this and the hydrogens coming off at 120-degree angles. So it looks like it truly represents the geometry. Can't do that with tetrahedral on a 2D surface. And then lastly, we have a triple bond between the carbons here. We'll worry about the names later. It's ethenes and ethynes. We're just changing the vowel, right, from A to E to Y. So this carbon here is still making 4 bonds, right? 3 of them to a neighboring carbon with a triple bond, and then 1 to a hydrogen. What is the geometry around that carbon?
Linear.
Exactly, it's linear. So again, no lone pairs. Carbon, from your purposes, will never have a lone pair. And so it only has 2 Vesper groups. And exactly how it's drawn is the geometry. It's flat, it's a straight line, and it's 180 degrees. So of the 3, this is the only one drawn most appropriately to represent its actual geometry. This one's almost there if we get these angles right. For this one, you can't represent its geometry on a 2D surface, at least not without using some kind of 3D mechanism like a wedge or a dash or something. Okay, so that's how we put those together, and you notice every case carbon always has 4 bonds. But there's more than one way to have 4 bonds. You could have 4 single bonds, you could have a double and 2 singles, you can have a triple and a single, and there's one more I've left out here. What's the other way a carbon can have 4 bonds? It's not shown on the screen.
A coordinate covalent bond?
No, that would still count as a bond, but what I'm talking about is how do I achieve a total of 4 bonds? The 3 ways represented are 4 singles, double and 2 singles, or a triple and a single. All those have a sum of 4 total bonds. There's one more way to do it, not shown.
2 doubles.
Two
double bonds.
Exactly.
2 bonds.
2 double bonds would also work. Not shown on the screen, of course, but that would just be another ethene-like molecule or alkene-like molecule with 2 double bonds in it. Right, we'd end up calling it a diene, 2 double bonds. We'll talk about that nomenclature in the future. Okay. The other things I want to show you on the screen here is what's actually happening with this double and triple bond. You had the picture last time on your previous slide, that slide set that showed the little cartoonish or mock-up with the Coke bottles and soda bottles and all that to show where the bonds are. But here again, we have a single bond is a sigma bond between the two, the direct connection there. Right, these aren't quite shown correctly because that's not direct geometry, but this is a single bond called a sigma bond between the two. When you have a double bond, it's drawn like this often, and this is how your model kits will represent it, but this is not really how it looks, right? It's not put together as two bending lines like this, and neither is a triple bond. They're just trying to show you, you can illustrate it this way as a single, double, or triple bond, but the geometries do not look like this. Okay, so when we have a single bond, it is a sigma bond, right? When we have a double bond, it's a sigma bond plus one pi bond. If you look back at your other slides, you'll see those illustrations. And a triple bond would be one sigma bond and two pi bonds. It doesn't really look like this in reality. Right? But in every case here, when you connect two atoms, the first bond is always called the sigma bond, and any ones above that, whether it's a double or triple, have a number of pi bonds, either one or two. And you can't have a quadruple bond because geometrically you don't have another direction in space to have a fourth bond. Right? And the last thing on this slide is this little colored picture I have here, and we're going to define carbons in their different classes. So here, I'd say a carbon is called a primary carbon. This arrow should be pointed to the carbon. That's really what I'm talking about here. I didn't draw this, but this arrow is pointing at the carbon. This carbon is called a primary carbon because it is bonded to exactly one other carbon. Okay, so this carbon here in orange, right, is bonded to exactly one other carbon. It is making four bonds. I know that's sometimes difficult to see here. You can see the one here going to the other carbon, but then it's making three bonds to hydrogen, like this guy is over here. Right? But it's just not drawn, it's written as CH3. And you'll probably see this when you get to your first or second lab exercise as well. There's different ways to represent these. You can do it with shorthand notation, just writing CH3. All three of these hydrogens are on that carbon. Or you can write it out like this, drawing every bond. Right? Or you can just do it as this is written CH2 and then write CH3 right after it without this line. It also means the carbon's bonded to the next one. These two H's in green are on this carbon. Okay? So what this means is this carbon, the orange one, is bonded to exactly one other carbon. There's lots of other orange examples of that here. So all of these four as well are primary carbons. Right? That's why they're drawn in the same color. The green one here is called a secondary carbon. And you could probably guess the definition. A secondary carbon, by the name alone, tells you this carbon is bonded to exactly two other carbons, this one and this one. And by the same rule, this red one is called a tertiary carbon because it is bonded to three other carbons, leaving only one bond for hydrogen. And at the top, the quaternary one in blue has no hydrogens on it because it's bonded to four other carbons. Right? I don't care what those other ones are, but it's bonded to four of them. Okay, so that's the difference between primary, secondary, tertiary, and quaternary carbons. So it's pretty easy to remember. If you have a tertiary carbon, then that carbon is clearly making three bonds to other carbon atoms, and there's only room for one other bond that would have one H on it. Secondary carbons would have two hydrogens not because it's secondary, but because this carbon is bonded to two other carbons, leaving only two bonds left for hydrogen. Similarly, primary carbons have three hydrogens because only one bond to another carbon, leaving three bonds for hydrogen. And of course, quaternary has no room left because there's four bonds to other carbons, no hydrogens. So it's pretty easy to pick those out. You can just count the number of hydrogens, subtract that from 4, and it'll tell you what type it is. Okay, so this carbon can exist bonded to hydrogen and other things, but what if we have just pure carbon? So one carbon bonded to four other carbons, right? And that's it. There's nothing else there. And sometimes it'll be bonded to only three other carbons, where one of the bonds is a double bond. There's still four bonds to carbon. There's no hydrogens there. Or sometimes it's arranged quite differently. So all those things I just described are made of pure carbon, but depending on that bonding structure can make quite different things. So the three things here, the diamond, graphite, and coal, you all know what a diamond is. Graphite is what's found in your, what they used to call the lead of pencils. It's not made of lead at all. It's made of graphite. It's pure carbon. And then coal is also made of pure carbon, which is a decayed organic remains where the only thing left is the carbon, right? everything else has been removed at that point. So it takes a long time to make those. So all of these structures, though, look like this. They're pure carbon in one form or another, right? So this is graphite. And what do you notice about this? If you look at any particular carbon atom represented by the spheres here, the gray lines are the bonds between them, any carbon here is connected to exactly 3 other carbons. One of those 3 bonds is a double bond. We never know which one it is. It varies. It can move around. But one of the 3 is a double bond. So that gives your carbon a total of 4 bonds, like it will always do. But because one of them is a double bond, it has trigonal planar geometry, right? 1 double and 2 singles, like we saw for ethene on the previous slide. So in that case, when all these carbons line up and every one of them is having the same type of geometry, it makes a nice flat plane. So you notice each one of these is independent of the others. It makes a nice flat sheet, right? That's all this does. Pure carbon, a flat sheet of carbon, right? It's a fairly strong sheet, but the neighboring sheet is not really bound to it that strongly, right? They're just sort of attracted to each other. They're not tightly bound at all, right? And then the one above that, and there's millions and millions and millions of these sheets put together, and that makes graphite. So if you take this material, it's not very hard at all, and you were to rub it on a surface, some of these sheets will flake off, and that's how you write with a pencil, right? Some of those sheets of carbon, many of them in fact, rub off on your page and stick to the page rather than the other sheets, and that's how you write with a pencil. How do you erase it? You use the eraser, which is just a rubberized abrasive, and it just rubs these sheets off the paper. And if you rub hard enough, you'll rip the paper, of course, but it rubs these sheets off the paper, and that's why it comes off. Right? If you rearrange it a little differently, looking at the bottom right here, now every carbon is making 4 single bonds to other carbons. So each one of these, as you see in the figure here, has this tetrahedral arrangement. It's easier to see in this image than it is in a drawing. This is made with your little model kits that you have in lab. So every carbon here is making 4 single bonds to every other carbon here, right? They're all following that rule. So they're all quaternary carbons, no hydrogens in any of these structures. If you put this together, this is just the opposite. Nothing here, if you try to rub it on something, is going to come loose. They're all very rigidly bound, and this is what makes a diamond. That's why it makes diamonds so hard, right? You can't scratch them because nothing in this carbon structure will fall off, right? It doesn't scratch. However, it will scratch many other things. It's the top of the line as far as the hardness scale. But they're both made of pure carbon, just a slight rearrangement of their structure. Okay? So what we're going to talk about for the first part of the semester is organic compounds, right? So hydrocarbons and their derivatives. We'll cover that in the first half of the course, basically, and then we'll move on to biochemistry after that. But the organic compounds, mainly all these carbons which may or may not have 1 or more hydrogens in them, and various derivatives of them. We'll make some modifications to it. We'll add some other elements, perhaps, like oxygen and nitrogen and sulfur. So those are going to be called hydrocarbon derivatives. We'll save those for later. They're going to be covered on your second test. But we'll start out with just plain old hydrocarbons. Nothing but carbon and hydrogen. And of those, we'll deal with the ones that are only carbon-carbon single bonded for now. So that's what we'll cover in this series of 3 lectures here for chapter 12. Only the ones that are single bonded. We'll leave the double and multiple bonds for later. Right? So let's talk about just the single bonded ones first. The very simple ones. So in order to do that, we need to introduce you to how we draw these things. So looking at this page, I drew 5 structures here. And one of these is not the same as the other 4. Right? So 4 of these are identical to each other. The molecules are identical. I've drawn them a little differently, but they're no different. Right? Because all these bonds, being single bonds, are free to rotate around each other. They're free to flop around and rotate on the bond-to-bond axis. So here we'll try to figure out which one of these is not connected like the other 4.
Is it the bottom one?
And why is that?
Because it touches 3 carbons.
Say again?
It touches 3 carbons.
So there's a tertiary carbon in there?
I think.
Yes, you're absolutely right. So this carbon right here is a tertiary carbon because it's bonded to 3 other carbons. You saw that right away. But in the case of all the others, we don't have a tertiary carbon. And that's because this molecule at the bottom is branched. That's what we call it. The other four are all identical to each other. And an easy way to see that, instead of trying to find all the tertiaries and secondaries and primary carbons, you could do that as an exercise. But an easier way to see it is, what's the longest continuous carbon chain I can make out of these? Well, the first one's trivial, right? It's all 6 in a row. It's the longest I can make. I can't backtrack. I can't go down 2 forks at once. Just find the longest continuous chain where you count from one end to the other, and I get 6, right? I get the same thing here. Whether this is bonded down or to the side, it doesn't make any difference. This bond can rotate. So this whole thing can rotate around all you want. Same thing for this one. I could have drawn quite a few more, right, for all the same molecule. But for the one at the bottom, the most you can get from one end to the other, and it's not always left to right or right to left or up and down, find the longest chain, is I can start at either one of these carbons on the left, right, these extremities, and I end up at the carbon on the right, or I start at the one on the right and end at either of these. But however I do it, the most I can get is 5. I can't get 6 in a row. That makes this a different molecule, right? So if I try to find these carbons, counting them, don't worry about what direction it's going in. That's not important. It's how many can I get in a row, not necessarily straight across. I might have to go up or down. But the most I can get in a row is how we're going to name these things. So this one clearly is not the same as the others, where all these are the same. There's 6 in a row. This is at most 5 in a row with a carbon branched off. Okay, so these other 4 are called different conformations of the same molecule. A conformation is just rotate a bond, twist it, bend it. You can do this with your model kits. Bend the, don't break it, of course, but rotate the bond around, and you'll see that you'll get all these different conformations, but they're the same molecule. In order to turn that into the one I've circled at the bottom, you must break a bond and reattach that carbon elsewhere. So if I imagine this straight one over here with 6 in a row, I pluck the carbon off the end and reattach it here, it would generate the one at the bottom. But that's not the same molecule anymore. If I pluck it off the end and reattach it on the other end, I regenerate the same molecule. So those are no different. But I have to do it differently. Okay? And we'll talk about what those things are called later. They're isomers of each other. But for now, I want you to see that these 4 are the same, and this one is different. Okay, so let's talk about these. How many ways can I draw it? This is termed isomerism. We'll talk about that word again later, what it means. But how many ways can I arrange it? So if I give you n carbon atoms, n being a number, and they have 2n plus 2 hydrogen atoms, that's the formula we're going to use. And let me go back and explain why that formula works. If n represents a number of carbons, it could be 1, 2, 3, 100, 6,000, doesn't make any difference. I'll always have 2n plus 2 as the number of hydrogen atoms if it's a saturated molecule. In other words, all single bonds. Okay, so let's go back and look at these at the beginning real quick. So at the very bottom we have our ethane, right? So every carbon in ethane is bonded to 3 hydrogens, right? There's only 2 carbons there. Every one of them is bonded to 3 hydrogens. You can see that rather clearly here. I want you to imagine an ethane that's much, much longer, right? An alkane that has many carbons on it. I don't care how many you imagine. Let's just do 10, for instance, right? But those 10 carbons in a row, much like I drew here, right? So this one only has 6, but imagine 10, right? A very long chain. Put that in your head. Every carbon in that chain, except for the 2 on the end, has how many hydrogens?
2?
2, exactly. They're all CH2s, right? They're all secondary carbons. Because they have to make 4 bonds, they're bonded to the previous carbon and the next carbon, and that leaves them only room for 2 hydrogens. So no matter how long your chain gets, if it's 1,000 carbons long, it doesn't make any difference. Every carbon, except the 2 on the end, has 2 hydrogens on it. All right, now what about the ones on the end? How many do they have?
3.
Why do they have 3?
Because they only have 1 bond to another carbon on each side.
Right, they're primary carbons. They're only bonded to 1 carbon because they're on the end. And then they need 3 hydrogens to fill the shell. But let me let you think about it a different way. If I discuss every carbon, including the ones on the end, they all have 2 hydrogens. And then there's 2 extra hydrogens. right? Because of the ones on the ends. Does that make sense to think of it that way? Every carbon has 2 hydrogens on it, guaranteed. The ones on the end each have 1 more. So it's 2 times the number of carbons plus the 2 extras. And that's where I get this formula. 2n, 2 times the number of carbons plus the 2, because the ones on the end have an extra 1. Right, 1 on each end. So that's why we get this formula 2n plus 2. And it doesn't matter if I do something like rearrange it at the bottom. It's still 2n plus 2. So if you get to the exam or you're trying to figure these out and you have to end up drawing these out, you're going to end up missing or miscounting the hydrogens. So don't do it this way. Don't draw everything. At first you might have to learn it, but by the time you get to the exam, you shouldn't be drawing everything. It just takes too much time. You don't have that much time. But use a formula. So in each of these cases, all of these have 6 carbons. How many hydrogens do they have? Every one of them on this page, including the bottom one. How many hydrogens?
Going to be 10.
So apply your formula. So we have 6.
14.
It'd be 14, right? So 6 carbons, which is 2 times 6 is 12, plus the 2 more gives you 14. So in every one of these cases, they have 14 hydrogens. You could go count them if you want, right? There's 3 on this end, plus the 2 here, 2, 2, 2, and 3. And that takes more time than just plugging into a formula. This one also works because this one has 3, 3, 1, 2, 2, and 3. Right? It still adds up to 14. But if you have to draw them and count them, it takes much, much longer than just applying a formula. Okay? So if n is
I have
1...
a question.
Sorry, you had a question? Go ahead.
Yes. What do we substitute for N?
N is the number
where do we get
of
the number?
carbons. Right? N is the number of carbon atoms. Then this formula, twice that number plus 2, gives you the number of hydrogen atoms. Let's do a few examples. If N is 1, right? N is 1, simple. 1 carbon, you know it's going to have 4 hydrogens around it. That's it. There's no other carbons. But does this formula work? If N is 1, you plug in 1 right here. 2 times 1, 2, plus 2, 4. Right? If N is 2, right? So we have 2 carbons now. You know that's ethane, where the carbons are bonded to each other. Right? Then each one is going to have 3 hydrogens on it for a total of 6. But your formula still works. If you plug in N equals 2, plug 2 in right here. 2 times 2, 4, plus 2, 6. Right? And that's the only way I can arrange these. There's no other way to arrange these atoms. 1 carbon by itself is trivial. It just sits there. If I have 2 carbons, there's only one way to connect those 2 carbons, and that's to each other. That's it. If I have 3 carbons, there's still only one way to do it, 3 in a row. If I take one off and try to attach it on the other carbon instead of this one, I still get 3 in a row. There's no other way to do it. And if I plug in N equals 3, it's 2 times 3, which is 6, plus 2, 8. There are a total of 8 hydrogens here. Okay? But when I get to N equals 4, I encounter a problem. How many ways can I connect 4 carbons? So the most obvious way, which you're all thinking of, is to put 4 in a row, and I agree. Is that the only way? Can you think of another way to do it?
You can do 2 double bonds.
Well, no double bonds. These are all single bonds. I'm just looking at how many ways can I connect the carbons.
You can have it like a branch off of the middle, like a chain of 3, and then a branch off of the middle one.
Exactly. So that wasn't an option before because it wasn't very diverse. But now I can do like propane there, 3 in a row, and instead of putting the 4th carbon on the end to make it longer, I can put it on that middle carbon. And now it's branched. How many hydrogens would it have?
It will still have 10.
It will still have 10, I agree. So you plug in N equals 4. 2 times 4 plus 2 is 10. Either way you draw it, either 4 in a row, right, butane on the left, or 3 in a row with 1 off the middle called isobutane on the right. All right, we'll talk about the names in a few minutes. But either of these still has 10 hydrogens. All right, so this is our first example of isomerism, right? These are isomers of each other. And what isomer means is you have the same parts, right? All the elements are still there, 4 carbons, 10 hydrogens in both cases, but they're put together differently, right? The connections are different, right? We didn't have that before because there was only one way to make the first three. But here we have two ways to put 4 carbons together. Okay? What about 5 carbons? How many ways can you draw it? So it's an easy algorithm to start thinking about this. How did you arrive at the 2 for butane? I said instead of putting 4 in a row, you can take off one and attach it elsewhere. So the obvious one for pentane is to put 5 in a row, take off the end, and try attaching it elsewhere. See what you can make, and see how many you get. There's no mathematical formula for figuring this out. You just have to draw them. Okay, so most of you probably have drawn the 5 in a row, right? Like that one. And then you took off the one on the end, either end, it doesn't matter. And instead of attaching it to the end, you attached it on the second piece, like we did before, right? But if I attach this methyl group, it's what it's called, the CH3. If I attach this carbon here or here, it's the same molecule, just flipped around, right? So you got to be careful not to repeat yourself. So if I take this 5 carbon piece, take the one off the end, and reattach it at one of the middle carbons, then I get this piece here. But attaching it on this one or this one was the same, right? So we don't want to repeat ourselves. It's just the molecule turned around. You got to see that in your head. But I can take this one and remove the one on the end again and attach it on the center to give you this type of molecule, right? So there's 3 different ways to put 5 carbons together. In every case, however, how many hydrogens will there be?
Well,
There'll be 12. Yes, it's 2n plus 2 again, n being 5 here. So these are the only 3 ways I can put this series of 5 carbons together, and these are all isomers of each other. But like we said before, if we go back, I was calling these methane, ethane, propane, butane. But when I had more than one, I can't just call it butane. I got to give it a new name, right? So we called this one isobutane. And then if we do it with the 5 carbons, we have pentane and isopentane. And then we needed a new name, so we called it new pentane or neopentane. And this is getting out of hand because if we move on to 6, how many are there? Well, this starts getting large quickly, right? There's actually 5 ways to do this, right? So we went from only having 1 to 2 to 3, and now there are 5. And if we keep growing, this number gets very large very fast, right? It becomes in the thousands to millions rather quickly. And this is the reason why there's those 9 million organic molecules, because just a few carbons can result in many, many different molecules, right? So this is why there's such a large group.
I have a question.
Okay.
Okay, so for pentane, you said we moved the one at the end to the second carbon. Isn't that going to change? Instead of CH2, wouldn't that just be CH?
It will be, and that's what's written down here. And I purposely left it in here. That was coming up on the next slide, a question that there was a mistake in one of these slides, and you caught it already, which is excellent. I do that on purpose for those who come to class, because some people don't. But yes, this should just say CH, and there's 2 ways you could have caught that, which I don't know which way you caught it, but you did, which is excellent. So if you add up the total number of hydrogens, we said it should be 12, right? And this does not add up to 12, right? This gives me 13. And if you count the number of bonds to this carbon, right, there would be 1 to this carbon, 1 to this one, 1 to this one. So this is a tertiary carbon, and then 2 more H's on it. So that would be 5 bonds to carbon, and that can't happen. So you're absolutely right. This should just say CH, no 2 here. Right? So I was going to ask that in a couple slides, but you beat me to it, which is excellent. Right, so for those who are not in class and watching the recording of this, pay attention to that. This should not be CH2, it should just be CH. And you'll find a few more of these that I've hidden in the slides as we go along. And how about hexane? So if you try hexane, there's 5 different ones, right? But if we draw them all out, we can't call them all hexane. We can't keep giving them weird names. We need some systematic way to accomplish this. So what we do is we start naming the substituents, right? Naming the things on the main chains. And if you think back, I told you, we're not just going to count all the carbons. We'll count the longest continuous chain, and that'll give it its name. Okay? So for example, here we have to learn these 10 names. It's only 10 you're going to need for this. I don't care if you learn the names for anything longer than 10, but I won't use them in class or on exams if it's longer than 10. You get the idea. But you got to learn these 10 names. And they follow a sort of easy thing to remember. Some of them are harder for other people, depending what your first language is. So if your first language is one of the Romance languages, you have no problem with 7. If your first language is English, 7 is a difficult one because we don't call it hept, we call it 7. Right? So methane, ethane, propane, you just got to remember those. Methane's 1 carbon, ethane 2, propane is 3, butane's 4, and then they start following the traditional Latin alphabet or Latin language where it's pentane, hexane, heptane, octane, nonane, decane. Right? So 5, 6, 7, 8, 9, 10. Right? It's sort of the way we do months as well, right? Except those were all messed up by Julius Caesar and Augustus. But 1 through 10, know these prefixes. They all end in ane. That just gives you the fact that it's an alkane. Alk is the generic term for this. It means just a carbon chain. And it's 1 through 10, learn those prefixes. Okay? Simplest version of these are drawn on the right. We can draw them like the top figure. It's methane. You see it's 1 carbon with 4 hydrogens on it. This one is kind of drawn in the 3D arrangement where you can see they're not right across from each other. Right? And then ethane, sort of drawn that way, giving you an idea of its tetrahedral geometry. Or you can simply draw ethane as a line. And this is called the line angle formula. And it's where you draw a line represents a bond, and atoms are indicated to be at the ends of lines or at the intersection of lines. The lines themselves are not atoms. The lines represent bonds. So ethane would simply be just a straight line. And at the ends of the line are represented the carbons. We don't generally talk about the hydrogens. You know they're there, and you know how many are there. Because if I draw the structure, say for pentane here, right? You see this here, this is pentane. How do I know it's pentane? Because there are 5 carbons. There's the one at the end, number 2 here, number 3 in the center where it goes down, number 4 where it goes up, and number 5 at the end of the line. There are only 4 lines because there's 4 bonds between the carbons. But there are 5 carbons here. So when you're drawing these, the common mistake I see all the time, and don't worry if you do it, everyone does it the first time. So if I ask you to draw, say, pentane, right, and people put down their pencil, right, as soon as they put it down, they draw a line and they say 1. Well, you've already drawn 2 carbons by drawing that line. So when you put your pencil down, as soon as it touches the page, say 1. Then when you draw the first line, you're on number 2, 3, 4, 5. Right? If you draw the line when you say the first number, you're going to draw the incorrect number of carbons. Right? So if you were to put your pencil down and go 1, right, or like this, 1, 2, 3, 4, 5, you've actually drawn 6. Right? So when your pencil hits the page, call that number 1 because that's the end of your line. Then as you draw the first segment, you're on number 2, 3, 4, and 5. Right? So keep that in mind. And that's why if you draw just a single line, it represents 2 carbons. We can't really draw methane that way because it would just be taking your pencil and putting a dot on the page. So it's kind of hard to draw methane that way. And that's why it's drawn like this. Right? So as you draw these, you notice they're all straight chain all the way from 1 to 9 here, but you can draw decane as well, just add one more line. And these are the ones I want you to know. The other way to write their names or write their formulas is in this structural formula here. Right? You'll learn the differences in lab. Right? This one's CH4 because it's a carbon with 4 hydrogens on it. Ethane is a pair of carbons. They are bonded to each other. We write the things that belong to this carbon after it. So this carbon has 3 hydrogens attached, and then it's attached to the next carbon, which also has 3 hydrogens attached, like in the figure. And I asked you to imagine that long one earlier with 10 carbons, and this is what you had in your head, right? This thing here plus one more line, and this thing here, where the carbons on the end had 3 hydrogens, and every one in the middle has 2, and that's represented in this shorthand. You could write each one out if you wanted to, or you could represent it as there's a CH2 4 times here. So this thing in parentheses happens back to back to back to back 4 times, or 5, 6, 7, or 8 times. So if I counted the number of carbons here in this decane, I know there's 10, there's the 8 CH2s in the middle, and the 2 CH3s on each end. 8 plus the 2 carbons makes 10. How do I know this has 22 hydrogens? I'm not going to count all these hydrogens. I plug it into the formula. 2 times 10 plus 2 is 22. Right, so this is the structural formula showing you how they're put together. And this is the molecular formula, where it's just a summary of the parts. There are 10 carbons and 22 hydrogens. That's all molecular formulas are. Just a summary. It doesn't tell you how they're put together at all, except maybe the first one. Right? But these tell you how they're put together. This could be redrawn in a line angle diagram over here on the right. So I tend to draw them in the line angle one so they're not so cluttered. And it's pretty easy to count the number of carbons. And you automatically know, say on these carbons here, it has 2 hydrogens. You did that earlier for me. Okay, so that's what I'm talking about here, line angle. Let's look at some examples at the bottom here. And don't make these mistakes. So it's very important that you remember, lines are bonds. The only place that real atoms exist are at the ends of lines or at the intersection of lines. Okay, so this molecule on the left is exactly the same as the molecule on the right. They are the exact same thing, drawn 2 different ways. So often you'll see drawings, and I don't like doing it this way. I'll do them like the one on the right because it's very simple and easy to understand. But if you're looking at it on a website or a review site or something else, or in a textbook even, they sometimes draw it this way, where at the end of the line they'll represent the last one as a CH3. Right? That's the same thing as here. There is a carbon here with 3 hydrogens on it. I just didn't draw them. And it's perfectly valid, and this is true for all of organic chemistry as you're learning it. You don't have to draw hydrogens if they're on a carbon. They're understood. You must draw them on all other elements though. But if they're on a carbon, I don't have to draw hydrogen because it just clutters up my image. I know they're there. So here you can draw the last carbon. You could even have drawn this one if you read. You could have written CH2 here, right, to represent it, like we did back here, right, CH2s. But you don't have to, right? So I like using the one on the right, but keep in mind when you're counting this, there is a carbon at the end. So this would be 1, 2, 3. You don't count lines. Lines are not atoms. Lines are bonds. Okay, so keep that in mind. Right? So let's look at some what would be called substituents. Right? So I got you to learn what to count and what not to count, but let's look at substituents. If I have a straight chain of 10 carbons again, just in a row, 10 carbons, straight in a row like the little jagged line we saw, there's no substituents. All 10 carbons are in the same main chain. Because if I asked you to find the longest continuous chain, we'll talk about the rule in a second, you would count all 10, because that's the most you can get. But often, like I started on the very first slide, you can't get all of them in the main chain. You told me it was branched, it was sticking off to the side. That's called a substituent. Anything I can't get in the main chain, we'll call a substituent. Think of them as jewelry hanging off of the main chain, right? So they're wearing things, right? And the things they can wear, we give them names, right? And it's based on the parent name. If you only had 3 carbons in a row, we would call that propane. You memorize that name back here. 3 carbons in a row, propane. Okay, very simple. It looks like this. But if there's something sticking off the main chain that's 3 carbons long, we'll call it a propyl group. So propane became propyl. And you're going to notice learning organic chemistry is treat it like learning a foreign language, right? Because it truly is a foreign language. Learn the endings of words. If it ends in ane, it's a noun, right? It's the main chain. If it ends in this YL, right? Think of this as an adjective. It's jewelry hanging off the main chain. So propane became propyl. We dropped the ane ending and added YL, right? So propyl is a substituent or a jewelry off of the main chain. If it only had 2 carbons, we'd call it ethyl from ethane. If it only has 1, I mentioned this earlier, I called it a methyl group, right? From methane. There's only 1 ane in the molecule, right? It's the main chain. But after that, we name the substituents. And we'll look at some examples. If they're not just straight, if they're kind of branched themselves, they may get some other interesting names. And we'll talk about those in a minute. Okay? So looking at some simple ones, here's methyl. I'm using this little wiggly line over here to represent it's some very long main chain, right? I don't know how long it is, and it doesn't matter. But it's clearly the main chain. That's all that represents. So it's a shorthand way of saying this is the main chain, and there's clearly something sticking off of it that's not in the main chain. There's no way I could have counted this carbon when I was counting the longest chain. That's all this means. So we call this 1 carbon side branch a methyl group, right? This is what it looks like. If I had 2 carbons there, it'd be an ethyl group. 3 carbons, propyl group, right? These are very simple, and they just get longer and longer and longer. And you just change the ending from ane to YL, right? It could get very, very long. However, if it gets very long, it's probably going to get longer than this main chain over here, right? Then it would not be a substituent, it would be the main chain itself. So keep that in mind, that your substituents can't be longer than the main chain, because by definition, the main chain is the longest, right? What if this group, since we had 1, 2, or 3, we now have different ways to draw this. Instead of drawing 3 in a row here, I could have branched this one, right? So coming off the main chain, this has 3 carbons, so does this, but instead of doing 1, 2, 3, it does 1 and branches into 2. So it splits, like split ends, right? Instead of having just one hair here, this one split into 2. Right? It's got a fork at the end of it. So we call that an isopropyl group. We could have a butyl group, right? Butyl is simply 4 in a row. I could represent it by adding a 4th carbon here, but I'm showing it to you a different way. So a butyl group here would be like this group, right? So there's 1, 2, 3, 4 sticking off, right? So just like this, 3 in a row, but in this case it's 1, 2, 3, 4 in a row. And there's multiple ways to draw that. In fact, there's 4 ways to draw it. I can draw it 4 in a row. I can draw it as an isobutyl. Again, it's 1, 2, and then it splits at the end. When you see that prefix iso, it generally means you split at the end, just like this one split at the end. So here it's 1, 2, 3, and 4 split, isobutyl. Or if you split it a little earlier, if it branched earlier, it branches first, and then one end is longer than the other. It's called sec-butyl because it branched at the 2nd carbon. Or it's called tert-butyl in this case because there's 3 things coming off the end, like a little bird's foot coming off. So it still has 4 carbons, so 1, and then 2, 3, 4. They're not in a row, and it's commonly called tert-butyl for tertiary butyl because there's 3 things coming off. That might seem confusing because this carbon is actually a quaternary carbon. Okay? But all of these in general, these are just a few of the common examples that we'll do. These are the most common ones, by the way. They're all called alkyl groups, right? Alkyl here. It comes from alkane again, just like I did with all these names. I dropped the ane ending from alkane and added the suffix that gives you the adjective form. And all of these groups have a particular number of carbons and hydrogens and so forth, but we can also represent them by just the letter R. R just means some length of carbon sticking off. So it's called an R group or a substituent. Just R is a generic placeholder for some number of carbons. Okay, we'll see that quite often.
I have a question, please.
Yeah, go ahead.
What do you mean by sticking off? When you say something is sticking off the carbon, what do you mean?
So let's go back up here. So here we have 6 carbons in a row, right? There's no substituents on this. All 6 carbons are in the longest possible chain I can count. And that's true for all 4 of these drawings. But the one at the bottom is not. The longest carbon chain I can get here is 5. So it's either 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. However I do it, the most I can get is 5. So if you want to think of it, this one is the longest chain. It's not always the horizontal one, but we can use that example. This carbon sticking off below is a substituent. It's not in the main chain. That's what I mean.
Okay.
And in this case, this would only be 1 carbon long, right? The substituent is a methyl group. Whereas the longest chain is 5, so this would be a pentane, not a hexane. It's only got a longest chain of 5. It does have 6 carbons, I agree. But when we name it, we're going to talk about the longest chain. I can't get this one in that chain. Does that make sense?
Yes,
Okay.
it does. Thank you.
And that's a good question because it's exactly what we're about to do. I'm going to talk about how do you find the longest chain, and then you start naming these substituents. And I also have to tell you where they are. They're going to need some addresses. So that's what we're going to do next. Okay. So we have the common ones we'll talk about. Common ones we'll use are methyl, ethyl, propyl, isopropyl, and all these butyl ones, right? The most common ones are going to be your methyls and ethyls, right? So let's do some
I have
rules.
a question.
Yeah, go ahead.
So you determine what the substituent is, like if it's methyl or ethyl and so on, based off how many carbons are sticking off of the longest chain?
That's correct.
Okay,
Right. And we're going to do exactly that. A few examples of that right here. But good question. Okay, so I listed the rules here for you, so you have them on a single sheet or page and learn them. And then I'm going to give you a simple shorthand version of these as we do some examples. But let's go through the rules real quick. And these set of rules we're going to use the whole semester. We're just going to add some twists to it as we go along. But these rules will still be in place. So rule number 1 is always the same. We're going to identify the longest continuous carbon chain. Right? So find the longest possible chain, keeping in mind that it may not be simply left to right on the page or right to left or up or down. Right? It can weave all over as long as you don't backtrack or jump over carbons. So find the longest continuous chain and name it. And by name it, I mean if it's 6 carbons long, you're going to call it hexane. If it's 9 carbons long, nonane. If it's 10 carbons long, decane. If it's 2, it's ethane, and so forth. You've learned those 10 prefixes. Okay? Once you've determined the longest continuous chain, let's find out any substituents that are on it, right? Things sticking off the chain, like you just told me, they're the number of carbons sticking off the chain. I gotta know what they are, right? So I locate them, right? I gotta number this chain, however long it is, from 1 to X, whatever the number longest chain is, and then I gotta locate the substituents, right? And I'm gonna give them numbers based on the end that they come from, right? I'll do an example and explain what that means. So I'm gonna locate them and number them, all the substituents groups. And then I'm going to place the prefix of that number and name in front of the parent chain. And we'll do several examples of these. If you have multiple identical substituents, like there's 2 methyl groups, right? We don't call it a methyl-methyl, we call it a dimethyl. We use the Greek numerical prefixes like di and tri and tetra and penta to name the number of those things, right? So if you had 4 ethyl groups, it'd be a tetraethyl, right? Tetra meaning the Greek prefix for 4, ethyl telling me what I have. And we'll do an example of those as well. Once you have all these parts listed, we have the main chain, we've named it, we've got all our substituents with their names and their locations, we list them in alphabetical order, right? And we ignore all those dis and tris and tetras and pentas as far as alphabetizing. But if you use a unique name like iso or neo or something like that, then we do alphabetize those. And these are really the only 2. Right? And then finally we have some punctuation. I need to separate in the long name that we're going to get any numbers from each other. If there's a series of numbers in a row, we separate numbers by commas. And if we separate numbers from location or numbers from words, locations from words, by dashes or hyphens. Okay? There are no spaces anywhere in this name. Right? Nothing at all. We don't add any spaces. But in between numbers we put commas, and in between numbers and words we put dashes or hyphens, right? So let's do a couple examples. I'm going to shorten this and show you one rule at a time as we do it. Okay. So the first thing to do is find the longest continuous chain. So here's an example. I threw up our molecule from earlier, keeping in mind that I may draw these as just lines that end without drawing the C here. I'm just making it easy for you to start. Find the longest continuous chain here, right? Keeping in mind it may not be the straight across chain. So what's the longest chain you guys can get? So think about it for a second.
It, 10 probably.
10, good. So if I try this, I only get 6 that way, right? Numbering, that's clearly not going to be the longest. If I do it this way, I get 9, right? If I count that way, I get 10. Right? And you may have gotten that same one, right? But I could also name it now, right? There's 10, definitely. You may have started on the other end and ended on the right, and that's perfectly fine too. It's still 10 in a row, so we'll name it. There's no longer chain here, right? So we'll call it decane, right? So it's definitely a decane molecule. The question being now, is it the way you numbered it, likely 1 to 10, or the way I did it, 1 to 10? Which one's correct? So we have 2 options, right? So which one is it? I'll throw both of those aside. Which of these 2 is correct? Right? So I have to start looking at what substituents do I have, right? What things are on the molecule, right? So if it didn't have any substituents, I'd be done. It's simply decane. But it does have some things on the molecule. What do you see attached? Right? An easy way to do this when you're learning how to do it, doing problems and examples, is when you finally identify your main chain, I like to take a pencil or a marker and either highlight it or circle it so you know what you've named already and what you have yet to name. So in this case, I would circle all these carbons, leaving out this thing, right? And go through here and circle all of this. Right? So I would leave this 1 carbon thing here, and my line when I'm circling would go through this bond, because a bond is not a carbon, but then it leaves 1, 2, 3 carbons sticking out here, right? So what substituents do you see?
There's a propyl group and a methyl group.
So there's a propyl group, good, and either one, right? It's the same. 3 carbons we call propyl. And how do I get 3? I don't count this one. That's part of my main chain, right? That was carbon number 5 or 6, depending how you counted it. But this carbon is yet to be counted. This is a bond, it's not counted, right? It's not an atom. So here are the carbons, 1, 2, 3. And when you're counting substituents, this one, where it's attached to the main chain, is by definition number 1. It must be number 1. So this is 1, 2, 3, and this one is simply 1. Okay, so good. So we're going to number the carbon atoms, giving the lowest possible number to the first substituent. So using your method here on the right, which I'm not saying is right or wrong because it's perfectly valid at this point, if I start counting here and I get to 10, what number would the first substituent I encounter get? What is its address?
5.
5.
Yes, the methyl group would have an address or a location of 5. Using my method starting over here from the right to the left, what number would the first substituent I encounter get?
5.
5.
Still 5.
Still 5. So we don't have a clear winner yet, right? That's why I chose this as an example. If one was 5 and one was 3, we're going to go with the 3, and that's the way we would number it. Right? So I'm giving you a little complex example here to show you some features of all the rules. Right? So we're still at an impasse, right? It's tied. So which one do we choose? Well, we move on to the next substituent. So from the drawing here that you did on the left, if I start here, my first substituent was on 5. What number is the second substituent on?
6.
6, right? So here I'm doing, there's a substituent on 5 and then 6. Going from the other way, do I get better numbers? I still get 5, 6. So it's still tied. And then I'm out of substituents, right? Those are the only 2. So far, both of these are valid. Right? I haven't eliminated one yet. So both of them are perfectly fine. So let's move on. Right? I've identified the 2 substituents. You told me they were a methyl and a propyl in either case, and you told me where they were. The one on the left is at locations 5 and 6, and the one on the right is also 5 and 6. So I named them. Right? So we said we named the prefix, or so we named the substituent, and we prefix it with a number. Right? So on the left, I have a 5 propyl and a 6 methyl, and they're both on the decane. Right? You see the parts of the name there. You always start with the noun at the end, right? So it's a decane, and in front of it we put some adjectives. There's a methyl on 6 and a propyl on 5. So it's called a 5 propyl, because you told me from this end that's where we got to it, is a propyl on 5 and a 6 methyl. There's no 2 numbers side by side here, so no commas are needed, but in between numbers and words we always put dashes or hyphens. Right? So 5 dash propyl dash 6, because this is separating one from the next, 6 methyl, and then decane, no space here at all. On the right we did a similar thing. We have 5 methyl, 6 propyl, decane. Okay, so I followed the rules so far. They're both perfectly valid. The next rule is I use Greek prefixes to indicate multiples. Well, we didn't have 2 methyls or 2 propyls, so this step really doesn't apply in this case, right? Don't think of these as methyls. I know they look like it, right? Don't think of these as methyls. They're part of the main chain, right? Just because they're on the end doesn't make them a methyl, right? This one was not in the main chain. That's why it was. Another point of confusion I often see is people wonder why I wrote it CH3 here and H3C here and H3C here and CH3 here. And this is where I really want you to pay attention and do it correctly. This bond from this carbon to this group over here is to the carbon itself. It's not bonded to the H's, right? So don't write this as CH3 over here, because this bond is not to the hydrogen, it's to the carbon, and these are on the carbon. That's why it's on the left. It's generally written as H3C, much like H2O. You could write that as OH2 if you wanted to. But here we draw it this way so that we indicate it's connected to the carbon, not the hydrogens. Okay. All right, so next rule is put them in alphabetical order. Did I do that? So looking at these words, did I either one of these in alphabetical order, or do I need to correct either one of them? Decane.
The one on the left.
The one on the right is alphabetical.
Right, decane will always be at the end. I don't alphabetize that. That's the noun. I'm alphabetizing the substituents. So here I have a P for propyl and M and methyl, and those are backwards. M comes before P, right? But this one looks fine, right? I'm not putting them in numerical order. 5 and 6 I don't care about. That's its address. It kind of goes along with it. So I need to fix it that this is the correct order, right? Not the one that where the alphabetizing was backwards. So I had a reason to eliminate one of them, so I'm going to go with this one. Okay, so decane will remain at the end. And I got rid of the other one because it wasn't out in alphabetical order. I could have fixed the other one. If I go back a second, I could have written 6-methyl-5-propyl decane. That would be a perfectly valid name if I fixed this. Right? Or 5-methyl-6-propyl decane, because they were tied on where they were. Right? As an example, we'll use this one. Okay? Let's do one more. You guys work through this one with me. So follow the same rules. I know I don't have the rules up there anymore, but let's count the longest continuous carbon chain here. And what do you get? Keep in mind, it may not be the one that goes straight across. Right, did everybody get 6? Okay, so there's several ways you could have gotten 6. You could have used this top carbon and ended up over here, or the top ending up down here, or this one ending up here, or this one ending up there. So there's 4 ways you could have done it, and then counting them backwards and forwards, either of those ways. I just listed 2 of them here, but you definitely should get 6. I used the one straight across because it was easier to draw, but either one is fine. So what's its name? What's its parent name?
Sir?
Hexane.
Hexane, exactly. We're going to call it hexane. All right, so we'll build it on from there. All right, so counting it as hexane, do you see any substituents? Are there any carbons not accounted for?
Yes.
I see a few of them, right?
Methyl.
Yep, so there's a methyl here, there's a methyl here, and there's a methyl here. Right, same thing over here. So I have 3 of the same group. So what would you call that?
Trimethyl.
I agree. There's a 3 methyl group, so I'm going to call it a trimethyl hexane. Right. The only thing left.
Excuse me?
Sorry, go ahead.
I have a question real fast. What is the methyl? That's confusing me.
A methyl is a single carbon, right, sticking off of a main chain. So in these cases, I'm counting the main chain here, 1 through 6. If you circle all those, it would help you, right? Or highlight them, or use a marker, or whatever you want to do. But then you see that I've not accounted for these 3 carbons in the name. These 6 are in the main chain, but I have not included these pieces in the name of my molecule yet. So I've circled them here to indicate that I need to name these things. And since it's only 1 carbon long, right, we called it a methyl. On the previous example, we had one that was 3 carbons long. It was a propyl. Right, so
Okay, thank you.
and I have 3 of them, so I don't call it a methyl-methyl-methyl hexane. I combine that and just say trimethyl. There are 3 of them. But now I need to tell you where they are, because they could be in many places. Right? So I need to tell you the locations of those methyl groups. So doing the one on the left, what location do you get if you count the methyl groups?
2, 4, 5.
2, 4, 5. And the one on the right?
2, 3, 5.
One of those is better than the other. Which one's better?
Right.
The second one.
The one on the right. And why is it better?
Less
Have a smaller number.
The numbers are lower.
So I'm not talking about the sum, though. I just mean looking at the first number of each one, I have a 2 and a 2, right? The first substituent's on 2 in either case, so we're still tied. Then I look at when the second substituent, it's on a 3 versus a 4. 3 is smaller than 4, so we're going to go with the one on the right. I don't care how many more substituents there are. When I find a winner, I stop counting. Right? Mm-hmm. So in this case, I'm not going to do the 2, 3, 5. The 2, 4, 5. I'm going to go with the 2, 3, 5. Because 2 and 3 were better than 2 and 4 to start with. The fact that the other one was on 5 didn't matter. Everybody okay with that so far?
Yes.
Right.
Yes.
Okay. If you have trouble with that, walk through this again. Watch the video one more time. And try to figure out where I'm following these rules and when do I find a better answer. Okay? Here's one more. Now I took off the ones on the end to help you see it more like I'm going to draw it for you. Right, so find the longest continuous chain here. Keeping in mind it may not be the one straight across.
9.
9, right? So we call it nonane, right? So non is the prefix for 9, and we put the ane ending. And then, are there any substituents on this thing?
Yes.
There's something, and it's definitely on number 5. Everybody see that? No matter which end you count from, that thing is on number 5. So I'm going to call it a 5 something there. I don't know the name of it yet. Nonane. Okay,
Well,
so
what's the difference between isopropyl and isobutyl?
let's say again.
What's the difference between isopropyl and isobutyl?
Isopropyl and what was the last thing?
Isobutyl.
Isobutyl. So
Yeah.
isopropyl, those are more common names that we'll occasionally use. If you say isopropyl, that means there are 3 carbons, but they're not in a row. Propyl would mean in a row. Isopropyl means it has the split ends. Okay. Isobutyl means there are 4 carbons total in that substituent, but they're not all 4 in a row. Again, it has a split end. Okay, there was a slide a few back that showed the split ends for those.
Sec-butyl.
Butyl, right? This is sec-butyl.
This is
right?
sec-butyl, but that's not the only way to name it. If you'd like to use the name sec-butyl, I'm totally okay with that, as long as you know what it means. But there's a more systematic way to do it, and many people like the more, I'm following the rules, my way to do it. And depending on your lab instructor, they may require you to do it one way or the other. But technically, both are correct. But your lab instructor may be particular about the way they want it done, and just make them happy. So our question is, what is this thing, right? My solid black line here is representing our nonane chain. I'm not going to draw it over and over and over. But like you said, what is this thing sticking up there, right? It has a name. We could call it it's definitely 3 carbons long, because remember, this must be number 1, right? This, where it's attached, this carbon off here, that is by definition number 1. So starting here, without exception, that is number 1. What is the longest chain I can get? So 1, 2, or 1, 2, 3. I can't start here and count 4, because by definition on a substituent, you must start where it's attached, number 1. Okay, so 1, 2, 3 is the longest I can get. Okay, we'll get to the sec-butyl thing in a minute. Right, so this is 1, 2, 3, but then this substituent is wearing a substituent. Right, it's like your earring's wearing an earring. Right, so here's your body. You're wearing this thing, but this thing is a propyl group by its longest chain. It's wearing something. What is it wearing?
A methyl group?
It's wearing a methyl group, exactly. And where is its methyl group? I need its location. We said this thing is on number 5 of the main chain, right? But where is this methyl on the propyl?
1,
It's
number
on,
2.
It's on number 1, right? So this is
Oh,
1, 2, 3. So it's a propyl, right? We're going to substitute that in right here where this question mark is later. But the propyl's wearing something. So the propyl has an adjective, and that's a methyl. But where is it? Because it could have been out here on number 2, right? It can't be on number 3 because it would have made the chain longer. But it's right here, so it's on number 1, so we're going to call it a 1-methyl-propyl. So that is the name of this entire substituent. It's a 1-methyl-propyl. It's all like one word. Think of it that way. And this whole thing needs to get inserted where this question mark is. But that gives me a problem. Then I'm going to have this 5 sitting next to a 1. And they mean different things. The 5 tells me where this whole thing is on the main chain, right? The 1 tells me where this thing is on the propyl. So to avoid confusion, when I throw this in there, I'm going to have to put it in parentheses. Right? Does that make sense to everybody? If I didn't put these parentheses, you're going to go, what does 5-1 mean? That makes no sense to me. With the parentheses, it's easier to see that on number 5 is all of this. Right? This whole thing in parentheses is on number 5. And the only reason I'm using the parentheses is because I ended up with those numbers next to each other. So I don't confuse you. But you must do it this way. But interior to the parentheses, what does it mean? It means there's a methyl on the propyl, and it's on number 1 of that propyl. So this is kind of a self-contained thing in here, right? So there's a 1-methyl-propyl, there's a methyl on the number 1 of the propyl, that's this thing, and that whole entity is on number 5 of my main chain. And that's the systematic way of doing it. Find the longest chain of your substituent, find the longest chain, keeping in mind you must start number 1 here. And then that may be wearing substituents, and then that may be wearing substituents, and that gets really complicated. The other way to do it, some people like this method, the other way to do it is to recognize this as one of your common ones, and you called that a sec-butyl group, right? It's a common name for this type of group. But this whole sec-butyl thing needs to go where this question mark is, right? So that sec-butyl name could be put in for what's on number 5. But no parentheses are needed here because there's no numbers in this. It tells me on number 5 is a sec-butyl group. Right? So if you recognize this arrangement as sec-butyl, then you can call it that if you want. If you'd rather not memorize the sec-butyl name and just do the systematic way, then do it this way. Either way is perfectly valid. I'm going to tend to do it this way, the systematic way, when I write it on an exam, because it's a little easier to understand, I think, instead of memorizing another common name. So this tells me on number 5 of a 9-carbon chain, there's something, and that something is 3 carbons long. So I draw 1, 2, 3 carbons, right? Off the main chain, 1, 2, 3. We'll practice drawing in a minute too. And then on number 1 of the thing I just drew, put a methyl on it, and you'll arrive at the structure. Okay? So let's do just the opposite. I'm going to give you a name, and I want you to draw it. There's some rules about drawing it you must follow. So whenever you draw the molecule, like you're going to start with the parent name down here, you're going to draw a heptane first. Whenever you're drawing it, when you put your pencil down and start drawing, that's number 1, and you have to stick with your numbering scheme. You can't switch it around on yourself, right? So when you draw those 7 carbons of this heptane, and you're likely to draw them straight across 1 through 7, and there's nothing wrong with that. I might choose to draw them differently. I might draw it top to bottom, or right to left, or make it an odd shape. It doesn't make any difference. Just put 7 in a row. But when you draw them and you label it numbers 1 through 7, you can't change your labels after you start. It gets confusing and you'll mess up. So to draw this one, let's start with heptane. So draw 7 carbons in a row. So I'll draw them like this, right? From bottom right to top left. And you could have gone the other way. It doesn't make any difference. But I'm going to draw 7. You can draw them straight across if you want, a little zigzag 1 through 7. Right? So I got the heptane down, and then I follow these instructions. It says on number 4, put an ethyl group. Right? So on number 4, right here, I put a 2-carbon chain. Ethyl means 2 carbons. And I don't count this as number 1 because this is number 4 of the main chain. I need to put 2 carbons off of this chain. And at the same time, on number 3, I need to do something twice. You notice there's 2 numbers here and there's a die. So every time you have a list of numbers, you're going to have a prefix that matches those numbers. If there were 3 numbers here, there'd be a tri. If there were 6 numbers here, there'd be a hexa in front of it. So 2 numbers here, and they're separated by a comma. So on number 3, I need to do something twice. I need to put 2 methyl groups on number 3. So I put 2 methyl groups sticking off of number 3. Right? So here's my 4-ethyl. I attached a 2-carbon group off of there. You don't have to write CH3 here if you don't want to. You can just draw the line, which I'll tend to do. And on number 3, I need to put 2 methyl groups. So there they are. They're sticking off the chain. Right? And my still labels 1 through 7 are there. I kind of moved it around so I made these letters fit, but this is the molecule, right? A way to check that you've drawn it correctly is to cover up this name now and go name this thing. And I may have chosen the wrong chain, so this name may be incorrect when I give it to you. You can still draw it, but then I want you to correct the name if it's wrong, and it may often be wrong. Okay, so let's do another simple example. Here's 2-ethyl pentane. So what do you draw first?
5 chain.
5 carbons in a row. Excellent. So I'm going to draw mine like that. I know I didn't draw them straight across. You could have drawn it like this, straight across. 1, 2, 3, 4, 5. I just happened to draw it this way. Nothing wrong with the way I drew it. Right? And then on this thing, I need to do what?
Draw an ethyl.
And how long is an ethyl?
2.
2 carbons, and it's not 2 carbons because there's a number 2 here. That's not what that means. The word ethyl means 2 carbons, and its location or its address is on carbon number 2 of my main chain. So on number 2 here, I need to put 2 carbons sticking off. So that's what I've done. There's my ethyl group. Right? So 1, 2, 3, 4, 5, and I've put the ethyl group sticking off the side. Right? And I'm done. I've drawn it. But now I have to ask myself, I mean, it's drawn correctly, but is this the right name? And I'll give you a hint. This one is not. Right, where did I go wrong in naming this?
It's not the main chain.
I didn't choose the longest main chain. You're right. Right. So the longest main chain would be how long?
6.
Yeah. So I've drawn this incorrectly.
6.
This is the main chain, right? 1 through 6, and there's a methyl substituent, not 5 carbons with an ethyl. You notice I need to get more carbons in that main chain if possible. Now, why did I number it 1 through 6 left to right instead of right to left?
Lower substituent number.
Exactly. I need to give the methyl group the lowest number possible. And if I numbered from right to left, it would be on number 4, right? 1, 2, 3, 4. But if I number left to right, it gets number 3, so that's the better option. I'm going to go with that. So this name I wrote, 2-ethylpentane, is just wrong, right? You could still draw it, and I'll make sure I'll do them that way. If I give you a wrong name, you may not know if it's right or wrong initially, but you will be able to draw it. And then when you finish drawing it, analyze the name. See, did I make a mistake? Did I give you a name that's incorrect? In this case, I did. So here, 6 across would be called what?
Hexane.
It'd be called hexane. And on the hexane is a
3-methyl.
a methyl, and what's its address?
3, so it'll be 3-methyl
3-methyl
hexane.
hexane.
Right, and you would write that as what goes between the 3 and the methyl.
Dash.
Exactly. So it's 3-methyl hexane. Right. So I'm going to try to get you in the role of saying 3-methyl hexane, but the first few times we talk about it, I may ask you to explicitly tell me where the dashes and commas are because you're still learning how to do it. Once you get used to where the punctuation goes, I won't ask you to say it anymore. But I'm not trying to be mean. I'm just making sure you know where the punctuation goes at the moment, and it'll become second nature if you do a few of these. Okay. Right. So this is the correct name, 3-methyl hexane. So you may see problems like this on your exam, where I give you one and ask you to draw it, and then give me the correct name if it's wrong, or tell me that the name is right. And you'll see this on a lot of your practice tests that I gave you. Okay. So for your learning this before next time, I wouldn't get behind. I would go start working on some of those practice tests. Maybe grab some of the older exams from 7-8 years ago and look at those exam 1 drawing problems. They're generally at the end of the exam. And practice with those. Some of them you may not be able to do yet because we haven't talked about rings or double bonds or other atoms yet. But find the simple ones and try to work on those before next time.